Namaskara. In this session we will continue our discussions on amortized analysis. We are going to take a look at a way to obtain the amortized costs for the operations. We have already seen accountant's method or a banker's method. We will see a more interesting method. This is called the potential method. Okay, amortized analysis by potential method. So, here is the idea. I have initial data structure D0. I perform operation 1, I get into the configuration D1. Then I perform operation 2, I get to the configuration D2. In this way, after performing ON on Dn minus 1, I get Dn. And there are actual costs converting D0 to D1. You do operations and that is the actual cost. Alright. Now, I am going to introduce a function called the potential function on the data structure. So, potential function is a function from a configuration of it depends on the configuration of the data structure. Okay, from a D2 real numbers. Okay, usually it will be positive. Okay, positive real numbers 0 greater than or equal to 0. Sometimes it can be integers. In general we will call okay, this is potential, and normally potential of initial configuration will be empty. Before you start the program there will not be anything in the data structure, and the data structure gets built and operated during the execution. Initially it will be null, right. So, typically D0 will be null, and potential of D0 we treat it as 0. So, potential the intuitive idea behind naming it potential is as follows. If you are adding to the surplus, it is like increasing the potential. When you are taking away from the surplus, it is like using the potential energy to pay for or to carry out the operation. So, the potential will decrease because you are carrying out an operation, it does not add to the potential, it removes. But basically because to perform the operation you need energy, you need resource. So, intuitively when the potential function is positive, the potential difference between potential di minus potential di minus 1 potential di minus potential di minus 1. This can be viewed in the following way intuitively. Okay. If this is positive, okay, this is accumulation of potential adding to the energy. If it is negative, it is use of that energy, that much energy is used to carry out. Therefore, this potential difference is a kind of a balancing factor that we are going to use. So, we will define amortized cost AI as this number, the actual cost plus CI has converted, CI is the cost of performing OI, operation OI. Operation OI has converted DI minus 1 to DI. So, there is a potential for DI minus, this is the difference, potential DI minus 1. This is a change in the data structure configuration has happened. So, there are some numbers I associate with it, and when I associate those numbers and add to this Ci, then I get Ai. So Ai is purely a number that I have obtained from Ci by adding something. It could be a negative number, it could be a positive number, whatever it is, there is a quantity that I have added and got it. So the actual Ai depends on potential function. But one thing is interesting here. So if you consider sigma Ai, I equals 1 to n, that is going to be sigma Ci plus sigma I equal to 1 to n of V di minus V di minus 1. This is a telescopic sum, okay, dn minus 1, dn minus 1 minus dn minus 2 and so on, d1 minus d0. Therefore, this is equal to sigma Ci plus potential of dn minus potential of d0, but this is 0. Therefore, this is equal to sigma Ci plus potential of dn. But this is always positive. Our potential function is always positive. Even if it is 0, it is equal. If it is positive, you see that sigma Ai is greater than or equal to sigma Ci. This is the important property. I have defined new numbers a1 to an for c1 to cn by defining a function on the data structure and considering the difference. This is called potential after minus potential before, potential after minus potential before. Because you are doing the operation I on di minus 1 and you get di, the actual cost is Ci. This is what happens actually in the data structure. But I am associating a number with the configuration through a potential function and I interpret the change as release of energy or accumulation of energy. Okay, even if you don't consider that interpretation, it is potential after, potential of the data structure after minus potential of the data structure before, phi of di minus. Suppose I introduce these kind of quantities, then sigma Ai, this is the kind of thing I want, right. Therefore, if I choose the potential function in a clever way, then Ai defined in this way will be uniform, simple, and I will be able to calculate this sum. Of course, if you define a nasty potential, your Ai is going to be equally complicated and that won't take you anywhere. So it depends on the, notice that any potential function will define an Ai and that sigma Ai will be greater than or equal to sigma Ci. For any potential function this is true. So you have to very cleverly choose the potential function so that the sigma Ai is easy to compute and it is as close to sigma Ci as possible. That is where the ingenuity lies. But this is purely a mathematical analysis part. This has nothing to do with your coding or program. Your program is you have a data structure defined, you have operations defined, you implement it. But is that a good data structure? You need an analysis for that. But the analysis is stuck here because the costs are fluctuating and varying cost. So we need a very sophisticated mathematical tool, and that is what the amortized analysis does. So amortized analysis is introducing amortized cost through a potential function. you have to be very wise and careful in the definition of the potential function. Useless potential function or irrelevant potential function, every potential function will define AI, and that sigma AI will be greater than or equal to sigma Ci, as you can see here. But if AI is complicated and if sigma AI is also equally difficult to compute, there is no point in that particular potential function. So let us take the same example and define a potential function in this way for our push multi-pop stack example. Okay. The potential function of a stack is number of items in the stack. This is the configuration. For every data structure I am associating a number, which this is positive, number of items is always positive, so this is always greater than or equal to 0. For an empty stack it is 0. If the stack has got 15 items, it is 15, whatever is the number of items. Okay. It is the cardinality or number of items. This is the potential function. Now if this is the potential function, what will be the amortized cost? Okay. So let us take push x s. Suppose S cardinality of S is alpha. Okay. You are doing the push operation. You have S with alpha item, you have S dash after push. This push will have alpha plus 1 item because you have pushed X. You have performed this operation. The actual cost is 1 because you are putting 1 item, the actual cost is 1. At any given time you can perform the push operation. The actual cost is 1. What is the potential difference? Potential after is alpha plus 1, potential before is alpha, so this is 2. Therefore this is actual cost of push, this is the amortized cost of push. Actual cost is 1, amortized cost is actual cost plus potential difference, potential after minus potential before. Potential after is alpha plus 1. Whenever you have whatever the stack you have of that will have alpha element, alpha can be 0, it does not matter, but it has got some element and that will give you 2. Amortized cost of push is 2. What is amortized cost of MPOP? What is amortized cost of MPOP? Actual cost is minimum of cardinality of S and K. This is the minimum cost. This is the actual cost. Let us see the potential difference, because amortized cost is actual cost plus potential after minus potential before. Whenever you perform that, potential after minus. We will consider 2 cases. Cardinality of S is greater than or equal to K. In that case actual cost will be K because you have K elements. So MPOP K will, you have K elements, so you are going to throw K elements out, and therefore it is K. What is potential after? Suppose I have alpha element before the MPOP. Suppose I have alpha element in the stack, right. After the operation you are throwing away K, therefore this will become alpha minus K. So potential after will be size of the stack, which is alpha minus k, minus what is the potential before? Before performing the operation you had alpha items, and this is 0. AI is 0. AI is 0 in this case. What about the case when cardinality of S is less than k? If cardinality of S is less than k, the actual cost is cardinality of S, because minimum of these two is, this is the actual cost. What is the potential before and potential after? You have asked to throw k elements out, but you do not have k element, you have less than k element. So it will make the stack empty, therefore potential after is 0. Potential after is 0. What is potential before? Cardinality of S, that much element are there, and this is again 0. So you can see that AI is 0, or amortized cost of multi-pop, amortized cost of M-pop is 0. Amortized cost of push is 2. That is the reason why it worked. When I pay 2 rupees for push, you could take 1 rupee for your labor, but then there is a surplus. So for M-pop I could get it free, in the sense I did not pay anything, but I have already paid you sufficient money, there is a surplus from which you can take. You can peacefully take whatever is your labor cost, that much is guaranteed to be there. We have mathematically proved that it will be there. So you are well paid, you are paid for all the operations you have done. So how much you have earned? As many number of operations. How many rupees you have earned? As many operations you have done. What is the upper bound for that? You look at how much I have paid, either 2 or 0. So there are n operations you have done, for each one of them I have paid either 2 or 0, either 2 or 0. So maximum I would have paid you only 2n, and less than that is your actual earning, that is the actual number of operations. Therefore the total complexity is less than or equal to 2n was established in the accounts method in that way. Here I have proved amortized cost is 2 or 0 through a potential function. So I have the following result. Any AI defined through the potential function will have the property that sigma Ci is less than or equal to sigma Ai, and that is less than or equal to a sum of 2's and 0's. Maximum 2 will be all of them 2, which is 2n. Maximum, assuming for each operation you get, it is only, we have almost touching this bound 2n. Suppose I do push x1 yes, push x2 yes, push xn minus 1 yes, m pop s n minus 1. So I would have paid 2 rupees for this and 2 rupees for this and 2 rupees for all of them. This I will not pay anything, but in this 2 rupees you have taken 1 rupee each, and you will have 1 rupee surplus. So you will have n minus 1 rupee surplus. From this n minus 1 you can get paid for this, because it is going to take n minus 1. So though I pay 0, you take the money for the operations you have done. So for this sequence of operation you have earned 2n minus 2 rupees, which is less than or equal to 2n anyway, right. Up to this you can earn, but this is the maximum, this is the bound, upper bound. Okay. So, if I use some other potential function, you may get ai, but they may are junk values, you may not be able to simplify. For example, try the potential function phi of s equal to cardinality of s square. This is also a positive function. For this one also you will get some ai, those ai will act as an upper bound, no doubt about it, but that ai, those ai you are getting with this kind of a potential function will not be simplifying easily, it will be complicated and you may not go anywhere. So, this is not a good potential function, whereas this one has led to a beautiful potential function. Phi of s equal to cardinality of s turned out to be a very nice potential function. So, you have to use your ingenuity to arrive at a potential function, use the potential function argument to get. Therefore, intuitively you feel that what is, see you look at this expression ai equals ci plus potential after minus potential before. Therefore, this is wildly fluctuating, this is uniform, this can be anything. Therefore, this fluctuation is nullified by Pa minus Pb. The potential difference cancels that wild variation, brings to some number that is uniform, which is easy for us to add. Therefore, coming up with the right potential function is the ingenious part of the analysis. That is the strong mathematical part of the analysis, because the conceptual framework will work for any positive function. Coming up with the right potential function leading to good AIs, tight AIs, that is where the creativity lies. Okay? So, we will take a closer look at the splay trees and their amortized analysis in our next session. That will be mathematically very sophisticated and advanced, and we will take a closer look at them in our next session. Thank you.